Welcome back. So the last time we were in the process of proving the multivariable Taylor theorem. We reduced proving this theorem to a claim about the mth derivative of a one variable function. So at this point it's just a calculation. There's no more, there are no more deltas and epsilons involved. Yeah. So what we saw was that using the induction hypothesis, we saw that this was equal to this expression. Okay. All right. So at this point we need to differentiate this derivative with respect to t, which is not rocket science. We can simply use the chain rule. Right. So this will be, the derivative is with respect to the ith variable. And then we use the chain rule would tell us that you have to differentiate this with respect to the ith variable in h, right? So that would, this would be, rather this would be the derivative with respect to t of the ith component of this, which would mean that it is h raised to alpha divided by norm h, right? Okay, so that would then mean that the norm h's cancel out. So we are in a good position, but this is not quite enough. Right, why is this not enough, right? What do we really need? We want the right hand side to be the following. Okay, so we want multi-indices such that beta 1 plus beta 2 so on until beta n is m, right? Indeed, we are taking m derivatives of f here, we are taking m derivatives here as well. This is indeed if basically if you fix, so the point is fix the multi-index beta. Okay. So at this juncture, we note that if I is such that beta I is larger than or equal to 1. What is the multi-index beta? It's just a vector full of integers, right? And some of these integers can be 0, some of them can be larger than 1, right? Take an I, take an index so that beta I is larger than 1. Then you can write beta as alpha plus this vector 0, 1, where this is the ith entry. So all I am doing is the following. I need to relate a multi-index of size m with one of size m minus 1, right? So I need to separate out this beta. You can write it as a sum of two vectors, alpha, which consists of a vector of non-negative integers, that is integers which are positive but not necessarily strictly positive, plus 0, 0, 0, 1, 0, 0, 0. Indeed, the fact that this consists of non-negative integers follows from this assumption. Okay. Right, so fix such a beta. You can write beta as alpha plus such a vector in a variety of ways, because there could be multiple i's so that beta is larger than 1. Okay. So what can we do at this point, notice the following, that if you take 1 divided by alpha factorial times m, I claim this is beta I divided by beta factorial times m. Indeed, what is beta factorial, right? This is beta 1 factorial, beta 2 factorial, so on until beta I minus 1 factorial, right, beta I factorial, so on, times beta I. This is 1 divided by beta 1 factorial, so on until beta I minus 1 factorial, beta I and this, right? What is that? That is beta I minus 1 factorial and so on. But what is this? This is precisely 1 by alpha factorial times m, because this is the same as alpha 1, this is the same as alpha I minus 1, this is precisely alpha I. Why? Because alpha I plus 1 is beta I by definition of alpha. Okay? So in other words, if you fix your beta, right, then this will be this will be h raised to beta, 1 divided by m times alpha factorial is not quite 1 by beta factorial, but it is beta I by beta factorial, right, times m. So if you sum over all such I, right, this is sum over beta I by beta factorial times m, right? And what is sum over beta I times beta factorial by m? It is simply 1 by beta factorial. Yeah? The sum of all such beta i's is indeed equal to m, right? Why is the sum of all such beta i's equal to m? Because the size of beta is m, right? So you can then, so this, my point is simply that this summation, so actually, sorry, you also have a sum over I here. So this double summation is the same as this single summation. This is where I was getting at, all right? So that would prove what we want, right? All right, so then this would prove Taylor's theorem. There is a small subtle point here, and I actually invite you to think about what the subtle point is. Okay, at this point there is a slight subtle point, and I intentionally don't want to tell you what it is. It has to do with this equality here, okay, right? But nonetheless, the proof aside of this combinatorial property, so we now have the full strength of the multivariable Taylor theorem at our disposal. Okay, so what? So now how can we use it? The whole point of this Taylor theorem business is to prove the second derivative test, okay, in multivariable calculus. But the second derivative test in multivariable calculus is a rather complicated affair. Why? Because in one variable calculus you can simply ask whether this number is positive or not. In multivariable calculus you don't have a single number. You have a matrix. By the way, this matrix is given a name. It's called the Hessian of F, after the mathematician Hess, right? So what does it mean for a matrix to be positive? Of course, one has this naive notion of demanding that each of these entries of the matrix be positive, right? That naive notion is not useful for us, as we will see. It doesn't mean that naive notion is not useful at all. It is useful for, I believe, for example, even in some problems involving probability, correlations, climate change, and so on. That sort of a notion can be useful. That's called sheer positivity, but that's not what we will deal with. So we want to know what it means for a matrix. By the way, this is not any old matrix. This is a symmetric matrix. Okay. So this is a symmetric matrix, and we want to know what it means for a real symmetric matrix to be positive in a certain sense. In what sense do we want it to be positive in the first place, right? Okay. So before we go to this, the statement of this multivariable Taylor, the second derivative test, here is a strange phenomenon that occurs in multivariable calculus but does not occur in single variable calculus, and that's this. So take this example. So what's the gradient of f? That's 2x and minus 2y, right? When is it 0? It's 0 if x equals 0, y equals 0, right? Now let's compute the second derivative, the so-called Hessian matrix of f, which I'm denoting as h of 0. What's this? This is d square f dx square at 0, d square f dx dy at 0, or d square f dy dx at 0, or d square f dy square at 0. Yeah. So what's this? So this is simply the second derivative of this. This is 2 minus 2, 0 and 0. Now this is a very strange sort of an affair. The point is, the Hessian is invertible as a matrix. It's of course invertible, right? Because the determinant is minus 4, or you can explicitly find the inverse. But the point is, 0, 0 is not a local extremum. This is very, very puzzling. The reason is, in one variable calculus, if f double dash is invertible, which would mean that f double dash is not 0, so it's either strictly positive or strictly negative, and if f dash is 0, then we know for a fact that the point that we have is a local extremum. Yeah, we know this for a fact. However, here the Hessian, that's the second derivative, is invertible. First derivative is 0, and yet this is not a local extremum. Why is it not a local extremum? Because if you fix y to be 0 and you vary x, f is positive, right, and it's 0 at 0. So it increases if you, that is f of x comma 0 is larger than f of 0 comma 0. But if you fix x to be 0 and y to vary, so f of 0 comma y is less than f of 0 comma 0. So in other words, it's neither a local max nor a local min. In some directions it's like a max, and in some directions it's like a min, right? So this phenomenon does not occur in one variable calculus. Already it's a subtle affair. The second point is that, so such points are called saddle points. Saddle points. The reason they're called saddle because it's like a horse saddle. Let's not rely on my drawing skills, but if you were to indulge me, it's something akin to this. So in one direction it's increasing, on the other direction it's decreasing, okay? So it's like a horse saddle. All right, so now we need to state the second derivative test. To this end, we need to make a definition. A square Hermitian, if it's real, then it's simply symmetric, right? Matrix A is said to be positive definite if V dagger AV is strictly positive for all V not equal to 0. Okay. Likewise, it's said to be positive semi-definite if V dagger AV is greater than or equal to 0 for all V. Okay. So I'm allowing equality also. So for example, the 0 matrix is positive semi-definite. What's an example of a positive definite matrix? A silly example would simply be the identity matrix, right? Because V dagger identity V is V dagger V, which is mod B1 square plus mod B2 square plus so on, which is positive at 0 as long as V is not the 0 vector. Okay. So more generally, if H is diagonal, okay, recall that Hermitian matrices have only real eigenvalues, so these numbers are all real. Then positive definite, so what is V dagger HV? That's this expression. It's easy to see that the expression is simply this. This is 0 for all V non-zero if and only if all these are strictly positive, right? Why? I mean, this is simply V1 bar, so on it will be H V1 to Vn. So you can just multiply H with V and you get lambda 1 V1 so on to lambda n Vn, and then you take multiply it with this row vector to get this, right? So this is strictly positive if and only if each of these eigenvalues are positive. I mean, it's easy to verify this, right? Likewise, H is negative definite if minus H is positive definite, if this is less than 0 for all V not equal to 0, and likewise you have negative semi-definite. Okay. So the first non-trivial observation is if H is positive definite, right? So just a small point, I called it A here. I'm going to call it H from now on because we'll use the Hessian. If H is positive definite, okay, that means this is positive for all V non-zero, in particular for all norm V equal to 1. Okay? And in fact, these two are equivalent to each other. The reason is if you are non-zero, you can be divided by your norm and become norm 1, and this inequality will not change. Right. So this implies, in fact, that this is larger than or equal to C. Why is this so? Because norm V equal to 1 is a closed and bounded subset of Rn. So that means this is compact. So why is norm V equal to 1 a closed subset of Rn? I invite you to check. It's by definition, and you can prove that the complement is open. That is, norm V larger than 1 union norm V less than 1 is open. It's bounded, which means it's contained in a large rectangle, which is also easy to check. Closed and bounded subsets of Rn are compact. Continuous functions. This is a continuous function, right? Because it's a polynomial in the entries of V, right? In this case, it's Cn, of course. Cn is the same as R2n. Okay, so that doesn't matter. This is a continuous function in the entries of the real, in terms of the real and imaginary parts of V. As you can easily check, it's a polynomial. So which means that continuous functions on closed and bounded sets the continuous functions on compact sets assume a minimum. And since this is positive, that means the minimum value is strictly positive. which is the same as saying V dagger HV is larger than C times norm V square for all V. Why? Because you can simply multiply by the norm of V square on both sides and get this, right? Okay, so right, so what can we do with this? So here is the statement of the second derivative test. So the theorem is, let U be open, be an open set, and F from U to R be a CK function on U. Let A belong to U and gradient of f of A be 0. If h of A is positive definite, then A is a local minimum. If h of A is negative definite, A is a local, maybe I'll put a quote here, maximum. And if h of A is invertible but not definite, which means it's neither positive definite nor negative definite, that means A is a saddle point. Okay. Conversely, if A is a local min, h of A is positive, semi-definite. Okay. So this is the statement of Taylor's theorem. Notice we have a third possibility that we did not have in one variable calculus, right? So if you take the, if the first derivative is 0, right, and if you are, in fact, a C2 is good enough for us, but, right, C2 is good enough, but might as well assume it's CK in general, but for us actually C2 is good enough. Might as well just assume it's a C2 function, right. So then suppose A is this sort of a point, by the way it's given a name, it's called a critical point of f. Okay, it's a place where the gradient of f vanishes. Then if the second derivative is positive in the sense that the Hessian matrix is positive definite, then A is a local minimum. If the Hessian matrix is negative definite, it's a local maximum. If it's invertible, but it's neither positive definite nor negative definite, A is a saddle point. What's a saddle point? It's a point such that in a neighborhood, in any neighborhood of this point, there is one point where the function is larger than the value at A, and there's one more point where the function's value is less than the value at A. So both possibilities occur. Okay. So and the converse is also true in the following sense, that if you have a local minimum, then the Hessian is not quite positive definite, but is positive semi-definite. Likewise, if it's a local maximum, it's positive, it's negative semi-definite. Okay, so this is the statement of Taylor's theorem of the second derivative test. But the trouble here is, how do you, we can prove it of course, but the trouble is how will you use it, right? To use it, you will have to know when a matrix is positive definite or negative definite, and that is a more challenging affair. So how does one prove it? The proof is, although it looks rather formidable, it's not really that complicated. By Taylor's theorem, f of A plus h is f of A plus the gradient of f h plus d square f dxi dxj of some theta times hi hj divided by 2, right, where theta is on the line joining a and a plus h, somewhere on the line joining a and a plus h. Yeah. All right. So this is the Taylor theorem statement. Okay. But at this point, so by assumption f of a plus h is f of a plus this. Let's call this hij because it's the Hessian times hij divided by 2. Now, note one small point here. We've already assumed the gradient of f at a is 0, but if a is a local extremum, then automatically the gradient of f at a is 0. Why? By simply taking the one variable function g of t as f of a plus th, right? This one variable function assumes a local extremum at t equals 0. So the derivative at 0 is 0, right, which would mean that the gradient of f is 0. Why does that mean this? Because this is dot h for all possible h. And if the dot product with every vector is 0, then your function is, then your vector is itself 0. Why? You can, for example, take h to be one of the basis vectors, 1, 0, 0, 0, so on. That will imply that the first component of this gradient of f is 0 and so on. Okay. Okay, so this is an aside. We don't really need this, but I'm just mentioning it. Okay, so the first derivative test is rather easy in multivariable calculus. Okay, so that's why I didn't even bother with proving it. Okay, I already assumed gradient of f is 0. Okay, so suppose, so if we knew that this matrix h of theta was positive definite, then, or rather is positive definite, f of a plus h is strictly larger than f of a. Why? What is this after all? This is simply h transpose h of theta h. What is h of theta times h? The ith entry of this is hij times j. H transpose times this is precisely this, right? And H is a real matrix which is symmetric, so it's, in particular, it's Hermitian. So if this is positive definite, which means this is strictly positive for all non-zero h, that means f of a plus h is strictly larger than f of a for all non-zero h. Okay, which would mean non-zero h in a neighborhood such that norm h is less than some epsilon, which would mean that a is a local min, right? The trouble is this phrase. What we have assumed is h of a, the Hessian at a, is positive definite. How do you know that the Hessian of theta is also positive definite? Note that the same problem occurred even in one variable calculus. If f double dash of a is positive, how do you know f double dash of theta is positive as long as theta is close enough to a? Notice that this epsilon is some fixed positive number, but it can be very small if we want, right? It's a local minimum after all, right? So if f double dash of a is positive, f double dash of theta is positive for all theta close enough to a. Why? Because of continuity of f double dash. We want a similar property to hold for matrices as well, but it requires a little bit more of work because it's not as simple as merely knowing whether a number is positive, right? So here we need a lemma. Okay, right. So how does what's this lemma? A real symmetric matrix. So this linear algebra lemma serves two purposes. It tells us how to show that a matrix is positive definite, and it also tells us the property that we want, that if you are positive definite at one point, if you move the matrix at a bit, that it will continue to be positive definite. If and only if all eigenvalues are positive, strictly positive. It's positive semi-definite if and only if all the eigenvalues are greater than or equal to 0. That is, equality can also be hold, right? Moreover, if H two symmetric n by n matrices, which is a subset of Rn square, is a continuous function, and if H of A is positive definite, then H of theta is also positive definite as long as theta is close enough to A, for all theta in an epsilon ball of A, for some epsilon positive. Okay, right. So this is the statement of the linear algebra lemma, which we will use in conjunction with Taylor's theorem to prove the second derivative test. We are out of time right now, so we will continue the next time, and then we'll finish the proof of the second derivative test, and I'll also give you an example of how to actually use it in practice. All right, so thank you for joining.